Hello everyone, in this video we are going to see about the representation of graph. We know that all data structures can be represented in memory in various ways, and here in this video we will see how the graphs are represented in various representation. So first one is the sequential representation. As the name implies, we are using the connectivity between the one vertex to the other vertex using the edges. Okay, so how it is done? In sequential representation, we use the adjacency matrix. So this is called as an adjacency matrix, where the adjacency is denoted by 1 and not adjacent, it means 0. So 0 represents the absence and 1 represents the presence. So if there is adjacent, we say it is 1. If it is not, means we are giving a 0. That is the adjacency matrix. And then we are having rows and columns which are represented by the graph vertices. So all the vertices are given both in the row wise as well as the column wise. Okay, so that means when you are having the 5 vertices, this matrix have n by n dimension. That is the like a square matrix. And then an entry mij is in the adjacency matrix of an undirected graph of G will be 1 if there exists an edge between Vi and Vj. For example, take this position 1. This 1 means there is a connection between B and D. So it is there. Okay, this is the point. Likewise, there is a connection between D and E. That means from the Dth row and the Eth column, 1 is there. This 1 represents D is connected to E. Yes, D is connected to E. And we can see here there is no arrows. That means A is connected to B, and we can say B is connected to E. So vice versa case is possible in the case of undirected graph. Whereas it has no direction. Okay. So for A, connectivity it's to B and D. So from A, B is 1 and D is 1. For B, A is 1, C is 1 and D is 1. A, C and D. For C, B and E are connected. So B has 1 and E has 1. For D, A and E. So D has A as connected and as well as B also here. Okay, D has 3 connections, A, B and E. So A, B and E, and finally E has connection from to C and D. So E is connected to C and D. So this is how the sequential representation is done for the adjacency using the adjacency matrix. Okay, next is the same adjacency matrix but for the directed graph. Directed graph means the graph has arrows, which means connection between A and B is directed. That means the flow that is from A to B but not B to A. That is called as the directed graph. Okay, so likewise from B it is to C and D. Likewise from C it is to E alone. From E it is to D but not to vice versa case, and for D it is to A. Okay, so likewise this direction has the meaning in the directed graph, which gives the connectivity also. Okay, so now here let us see with an example. A, B, C, D, E, the same graph, write the rows as well as the columns, and then from A we are going to connect B. Nothing is more is connected. Okay, so to A to B connectivity is 1. So put a 1 over here, remaining are 0. And then for B, D is connected and C is connected. So put a C in 1 and put a 1 in D, remaining are 0. Likewise for C it is connected to E. So for C you put a 1 in E, remaining are 0. Then for D it is connected to A as well, only it is connected to A. So put 1 in the A position, remaining are 0, and E means, and for E it is connected to D. So put 1 in the D position. So here this arrow has meaning, and it says that the connection flows from in the unit direction, only one direction. Okay, so this is the concept of adjacency matrix representation for the directed graph. Let us see the next slide, where we are using the weighted directed graph representation. As the name implies, the direction as well as the weight is associated with the matrix. Let us see with the example. The same matrix is taken, and but here the weights are attached here. So we are having the weights 4, 2, 5. These weights may be any values, like it may be unit of time or the cost or the effort, anything we can mention by the values. That is called as a weight. Okay, so we can see here from A to 4 there is a connectivity A to B is the connectivity, 4 is the value, so we are putting 4 in the B position because B is connected to A by weight 4. Likewise, B to C is 2 as well as B to D is 1. So B has 2 connectivity, so put 2 in C and 1 in D, and from C there is only to E, which is 8 is the weight. Okay, so C to E 8 is the weight, and for D only A is connected, so the value is 5 here. Okay, for A it is 5, but here this when we see as a D, we are having connection to A, B and E, but the direction is towards D in the case of B as well as E. Only A has connection away from D, so that is only the connectivity. Okay, so now the number of arrows that pass towards a node is called as an in degree, and number of lines that pass out is called as an out degree. Okay, for example, if we take the node of D, in degree is 2 because B and C falls in and D goes out, so out degree is 1 for D. Same way, if we say take for E, E in degree is 1 and out degree is 1 because 1 passes inside, 1 passes outside. Okay, so direction has meaning, and here the weight is also attached. So E to D is 10 is the weight, so E to D is connected with the weight 10. Okay, so likewise we have another representation for the graph using the linked list. We know that linked list has the data as well as the pointer nodes. So here they take the same example, A, B, C, D, E, same vertices, but the connectivities are a little different here. So from A we are having B and C. So A is the node and B and C has the connectivity. So we are using each and every vertex by the node and the pointer, which is the linked list representation. After C there is no connection, so you put a null pointer, which is the cross in the C position. Okay, likewise from B it is to D as well as E, so it is connected to B to D and then to E. After that there is no connection, put a cross. Then for C it is towards D only, it is towards D. Okay, so C to D and no more, so it is put a pointer, cross pointer, null pointer. And then for D we are having D itself. This is called as a loop or a cycle. Okay, so D has D itself as well as E as well as A. Okay, so D has A, D and E, and then the null pointer, and finally E has no in out degree. Okay, E has no out degree, E has only in degree. So 2 arrows fall in, but there is no connection which goes outside E. So E has out degree 0, so which is the null pointer over here. So that's all the concept of in degrees and out degrees, and how the linked list representation is done for the adjacency list. The same thing is done by the array concept. Instead of using the linked list, we are using the array as the representation. Same example in the previous slide, but the difference is representation is the array. So for reference, we are having 5 nodes A, B, C, D, E. So we are taking 0 to 4 as the array position to note all the vertices A to E. Okay, and accordingly the connectivity from A it is to B and C. So we are putting here another array which is called as an adjacency array. Okay, so B and C as the adjacency, and next one a B. So B has D and E, so write here as the array, and for next one C is the connectivity, so put D over here. Then for D we have 3 connectivities to A, to D itself and to E. So A, D and E, and finally E has no out degree, it has no connection outside, so we are using the cross to say it is a null pointer. So that's all how the graph is represented using the various representation like sequential list, linked list as well as the array representation of the adjacency matrix. Hope it is easy to follow, and thanks for watching.